Hello everyone, this is Muthuraj, Civil Assistant Professor of PSM College of Technology, shortly abbreviated as PSM set. And here just we going to see about theoretical key capsule for revising strength of materials. And first the topic going to begin with types of materials that we are going to see about. And in the tabulation form, I am separately partitioned as materials and descriptions, and on that materials first we are going to see about homogeneous material which have same elastic property at any point in a given direction is called as homogeneous material. And related to isotropic, these materials have same identical properties in all direction at a point, and as per our anisotropic material, it has different properties in all direction at a point in the body. And about orthotropic material, a material which has different properties in three mutually perpendicular planes. And now we are going to see about the types of material which are related with total number of dependent elastic contents and number of elastic constants and number of independent elastic constants. And about homogeneous and isotropic, there are 4 dependent elastic constants and 2 independent elastic constants. And on orthotropic, there are 12 dependent elastic constants and 9 independent elastic constants. And on anisotropy, there are infinity number of dependent elastic constants and 21 independent elastic constants. And here we are going to see about the Poisson ratio adapted for every material, and some more materials, not every materials. Here I given about some materials. They are of about cork it's 0.18, and on concrete it's 0.1 to 0.2, and on rough iron it's 0.3, and glass 0.02 to 0.3, and on cast iron 0.23 to 0.27, and on elastic materials 0.25 to 0.4, and on steel 0.27 to 0.33, and on rubber 0.5, and on human tissues which are dead or living -1. And now we are going to see about the dependent and independent elastic materials, elastic constants we seen on 2 slides before, and the constants belonging to that elastic constants are the modulus constants belonging to that elastic constants are Young's modulus or modulus of elasticity. E is equal to longitudinal stress by longitudinal strain. This is equal to sigma by epsilon is equal to FL by delta LA. Delta L is nothing but change in length. And shear modulus or modulus of rigidity, G is equal to shear stress or shear strain. And on Poisson ratio, nu is equal to minus of it's a negative one, minus of lateral strain by linear strain is equal to delta D by D divided by delta L by L, which means change in dia by original diameter and change length by original length. And finally bulk modulus K is equal to direct stress by volumetric strain is equal to sigma D by epsilon V, where epsilon V is equal to volumetric strain is equal to change in volume divided by original volume. The change in volume as we seen earlier as delta L delta D, here we are seeing about delta V by V, and is equal to sigma by E into 1 minus 2 nu. The relations between all the 4 constants on later slide is E, G, K and mu, and E is equal to 2 of G with the bracket of 1 plus mu is equal to 3 of K with the bracket of 1 minus 2 nu also is equal to 9 kg divided by 3k plus G, and mu is equal to 3k minus 2G divided by 6k plus 2G, and the K and G are K is equal to bulk modulus and G is equal to shear modulus. For any engineering material, mu the Poisson ratio which is within 0 to 0.5, maximum limit is 0 and minimum limit is 0, which is as per that bulk modulus and shear modulus E by 2 and E by 3, and for maximum limit 0.5, which is also E by 3 or infinity. Axial elongations in different types of bar. types of bars are prismatic, circular tapered and rectangular tapered and composite bars. And elongation due to external load, delta L is equal to PL by AE or sigma L by E. As well as for circular tapered bar, delta L is equal to 4PL divided by pi D1 D2 DE into E. And for rectangular tapered bar, delta L is equal to P of P into L into log E with the base E of B2 by B1 divided by B2 minus B1 into ET. And for composite bar, P is equal to P1 plus P2. Change in length, del 1 is equal to del 2 is equal to P1L by A1 E1 is equal to P2L divided by A2 E2. P1 is equal to A1 E1 divided by A1 E1 plus A2 E2 and the whole divided off and the whole multiplied with P2, and the P2 A2 E2 divided by A1 E1 plus A2 E2 and the whole multiplication of P1. Axial elongation, different types of bars continued as for elongation due to self weight. Previously we saw elongation due to external load, and now we are going to see about elongation due to self weight. For prismatic bar, sigma LP is equal to delta LP is equal to Y L square divided by 2E is equal to WL by 2AE is equal to small w, which is negotiated with acceleration due to gravity, and finally it came as rho GL by 2E. And uniform tapering or conical bar, delta LC is equal to WL by 6AE, which is finally negotiated as 1 by 3 delta LP, which is nothing but delta LP is prismatic bar. And prismatic bar due to external load and self weight, delta L is equal to PL by AE plus WL by 2AE. And just summation of previous two, so delta LP and delta LC. And the points to be remembered from the previous things: elasticity, EMS is equal to EHOSD and is equal to EHCS. MS is equal to mild steel, and HOSD highly yield strain deformed steel, and HCS is high carbon steel, and carbon and strength high HCS greater than HOSD greater than MS. And ductility, the decreasing order of MS, HOSD and HCS, and ultimate stress greater than yield stress greater than working stress. Modulus of velocity for different types of materials as seen here, and materials which belongs to Young's modulus: steel 2 into 10 power 5 and the unit is megapascal, and for copper 1.17 into 10 power 5, and for cast iron 1.7 into 10 power 5, and for timber 0.1 into 10 power 5, and for aluminium 0.7 into 10 power 5, and for gas 0.8 into 10 power 5. Here we are going to see about some important terms of stress strain diagrams, and as per any mechanics of any materials or behavior, the stress strain diagram was very important, and on that stress strain diagram there are some important terms which we are going to see now. The terms and its definition are partitioned as a tabulation here. The toughness, withstand stress without fracture, and proof toughness, maximum impact energy observed without fracture, and modulus of toughness, total strain energy per unit volume up to fracture, endurance or fragrance limit, stress level below which an infinite number of load cycles can be applied to a material without causing fatigue failure. And for creep, which is defined as time dependent and permanent deformation of a material when subjected to a constant load or stress. And for fatigue strength, when a material is subjected to cycle or repeated loading, failure occurs before the yield strength. And stiffness is related to the resistance of a material against deformation due to applied load. And on resilience, the important terms are continued as resilience, the strain energy stored due to strain within elastic limit by the elastic material. Proof resilience, the maximum strain energy stored by the material up to elastic limit without creating a permanent distortion. Modulus of resilience, proof resilience per unit volume is called the modulus of resilience. Relaxation, stress relaxation is the time dependent decreases of the stress in the material under constant strain at a constant temperature. Tenacity, it is the properties of material to resist tensile force without failure. Malleability, it is the property of material by which it can be beaten or rolled into plates. And now the points to be remembered as percentage elongation of ductile material is 20 to 30%. For gradually applied loads, resilience is equal to sigma square divided by 2E into whole volume, and for proof resilience, sigma P of square, which is proof stress, divided by 2E into whole of volume, and for modulus of resilience is equal to sigma P square divided by 2E, and sigma P is equal to proof stress, sigma is equal to stress is equal to P by A. For a suddenly applied load, sigma is equal to 2P by A. A suddenly applied load, instantaneously applied load causes twice the stress and deformation compared to gradually applied load of same magnitude. An engineer consider gradual loading condition for static and quasi-static structural analysis. Impact of shock loading requires additional consideration. Example, dynamic load factor. And gradually applied loads are simpler to analysis because they avoid dynamic effects and stress and relationship follows Hooke's law for elastic materials. Understanding this concept is crucial for designing safe and efficient structure. Various theory of failures in strength of material and machine design. Theory of failure are used to predict the failure of a material under complex stress conditions, which is multi-axial stresses as bracketed there. Based on its behavior under uniaxial tensile tests, these theories help engineers determine safe design limits. Maximum principal stress theory, also known as Rankine's theory, applicable to brittle material, example cast iron, concrete, ceramics. And for maximum shear stress theory, also known as Tresca's theory, applicable to ductile material, example mild steel, aluminum. And for maximum distortion energy theory, also known as von Mises Henschke, sorry, that's a spelling mistake, it's Henschke, Henschke theory, and most widely used for ductile materials. And maximum strain energy theory is also known as Beltrami-Haig theory. Statement: the failure occurs when the total strain energy per unit volume exceeds that of a uniaxial test. Maximum principal strain theory, also known as Saint Venant's theory. Statement: failure occurs when the maximum principal strain exceeds the strain at yield in a uniaxial test. Most failure theory, modified for brittle materials, applicable to brittle materials with different tensile and compressive strengths. Example, cast iron. For ductile materials, von Mises most accurate or Tresca conservative one. And for brittle material, Rankine is a simple method, and most theory if tensile and compressive strength differ from one another. Types of beam and strain energy. Types, description and example. For simply supported at both ends, free to rotate. And supports may be hinge and roller. It's a hinge and roller. The example of bridge beams and floor joists. For cantilever, fixed at one end and free at the other end. Example, balconies and diving boats. Fixed, which is also known as it's conditioned as encasted. Both ends rigidity fixed, no rotation or translation. Example, machine frames and heavy supports. Overhanging extends beyond its support on both one ends. Example, balconies, crane arms, etc. Continuous, multiple supports more than two, long span bridge or building. The important formulas we are going to see on further later, because now we have to see the outline of the content. The assumptions of pure bending or simple bending. The Euler we just seen about Euler-Bernoulli beam theory. Classical bending theory is based on following assumptions. The beam is initially straight, which means the beam is perfectly straight before loading, and any initial curvature would introduce additional stresses. Material is homogeneous and isotropic. Homogeneous means same material properties throughout its all the planes. And for isotropic, elastic properties are identical in all directions. Example, steel, aluminum. Hooke's law is valid. Linear elastic material, stresses proportional to strain within the elastic limit. Plane section remain plane after bending, that is Bernoulli's hypothesis. And cross section normal to the beam axis remains plane and normal after bending. No warping or distortion occurs. Bending occurs in the same plane. The applied moment causes bending only in one plane, example xy plane. No twisting or lateral buckling occurs, that is Z plane. Small deflection, linear theory. Deformations are small compared to beam dimensions and no shear deformation, negligible. The shear stresses are negligible. Uniform bending moment. The bending moment is constant along the beam length. Bending equation and torsion equation. The bending equation assumptions are plane section remains plane. It's only for pure bending, not for partial or no bending. It's for pure bending. The plane section remains plane. Material is homogeneous, isotropic and linear elastic. Bending occurs in a single plane and no deformation occurs. No shear deformation. Example Euler-Bernoulli beam theory. Torsion equation. The torsion equation relates torque, shear stress and angle of twist in circular shafts. And the assumptions of pure torsions are shaft is straight and of uniform cross section. Material is homogeneous, isotropic and elastic. And shear stress varies linearly from the center. Whereas shaft is subject to torsion and bending. Both normal stresses from bending and shear stresses from torsion act simultaneously. To analyze the shaft strength under these combined loads, we use theory of areas to determine the equivalent stress. Also know that equivalent stress field theory is also called as von Mises or maximum shear stress theory. Strain energy for various shafts. Strain energy is the energy stored in the shaft due to deformation under various loads, torsion, bending or axial forces. The formulas vary based on the types of loading and shaft geometry. The applications are machine design, calculating energy storage in crankshafts, drive shafts, and structural analysis determining resilience under dynamic load, and for failure prediction relating strain energy to yield criteria. Types of load and its shape of shear force diagram and bending moment diagram. Load type, shear force diagram shape, bending moment diagram shape, and maximum bending moment location. For the conditions of point load, the rectangular jump. For shear force diagram, it's a rectangular jump. For bending moment diagram, it's a triangular peak. For maximum bending moment location at under the load. For uniformly distributed load, the shear force diagram is linear slope and the bending moment diagram is parabolic, and for maximum bending moment location is location at midspan if symmetric. For uniformly varying load, the shear force diagram is curved, which is quadratic equation, solved with the quadratic equation, and bending moment diagram is cubic, and maximum bending moment location near higher load end. For cantilever end, the load applied at the end, which is free end, shear force diagram is constant and bending moment diagram is linear, and maximum bending moment location are located at a fixed support. Couple. No change in shear force diagram and sudden jump in bending moment diagram. At the couple location, the maximum bending moment will occur. Maximum shear force, bending moment, slope and deflection of various types of beams. The formulas are derived using integration methods or standard beam tables. Shear force is maximum at supports for distributed loads and under point loads. Bending moment is maximum at the center for simply supported beams and at fixed ends for cantilevers. Deflection is highest where the slope is 0, usually midspan or fixed end. Fixed beams have smaller deflection than simply supported beams due to higher constraints. Methods to determine slope and deflection. The methods are and best for advantage and its limitation. For double integration, it's best for simple beams and advantage are exact solution. Limitations are tedious for multiple loads. And on Macaulay's method, best for discontinuous loads, and advantages for handles point loads easily. Limitations requires singularity functions. For moment area, it's best for qualitative analysis, and advantages are no integration needed. For limitations, less precise for the deflection, and for conjugated beam method, best for indeterminate beams. Advantages are mimics real beam behavior, and limitations are support conversions tricky. For energy methods, best for complex indeterminate beams. Advantages are works for non-linear materials, and the limitations are needs fictitious loads. and finite element method best for real world structures, handles advantages are handles arbitrary geometries, and limitations are requires software. And related about column and other materials, we will see test some analytical formulas using the notes I provided in my hand. And now we are going to see about the various theory of failures in some with some extra words prepared by myself. For maximum principal stress or normal stress, which is also known as Rankine or Leibniz theory, which is suitable for brittle material, and graphical representation are represented using square. And for maximum principal stress, the principal strain theory, it is also known as Saint-Venance theory, material suitable for brittle, and the graphical representations are rhombus. And for maximum shear stress or stress difference theory, this is also known as Guess or Tresca's or Coulomb theory. The material best suitable for ductile, and the graphical representations are hexagon. The maximum strain energy theory, which is also known as Haig or Beltrami theory, material suitable for ductile, and the graphical representation are elliptical. And for maximum shear strain energy or distortion energy theory, which is also known as Van Mises or Hemke, the material best suitable for ductile, and the graphical representation also known as elliptical, as same to maximum strain energy theory. And for types of beams and its strain energy, for a cantilever beam, the strain energy is W square L power cube divided by 6 EI, and for a cantilever beam with UDL entirely over the length, it's W square L power 5 divided by 40 EI, and for a simply supported with the central point load, W square L power 3 divided by 96 EI. For a simply supported beam with the UDL over the entire length, W square L power 5 divided by 240 EI. And for a fixed beam with central point load, W square L power 3 divided by 384 EI. And for a fixed beam with the UDL over the entire length, W square L power 5 divided by 1440 EI. And for a couple of moment at simply supported, it's M square L divided by 2 EI. And now we are going to see about the important formulas. For a normal stress, sigma n is equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 with the into cos 2 theta plus tau xy sin 2 theta. And for tangential or shear stress, tau x is equal to sigma x minus sigma y divided by 2 sin 2 theta plus tau xy cos 2 theta. For principal plane, tan 2 theta is equal to 2 tau xy divided by sigma x minus sigma y. For principal stress, sigma max or minimum is equal to sigma x plus sigma y divided by 2 plus or minus the whole root of sigma x minus sigma y divided by 2 square plus tau xy of square. The radius of Mohr circle is tau max is equal to sigma max minus sigma minimum divided by 2, also is equal to 1 by 2 of whole square root of sigma y minus sigma x whole square plus 4 tau square xy. Center of circle, sigma x plus sigma y divided by 2 and other coordinates is 0. For maximum shear stress, tau xy is equal to sigma x minus sigma y divided by 2, and for minimum shear stress, tau xy is equal to minus of sigma x minus sigma y divided by 2. And the ratio of shear stresses for different cross sections, here are something the prepared via tabulations. For rectangular or square cross section, the tau max divided by tau average is equal to 3 by 2, and tau max divided by tau NA is equal to 1, and tau NA divided by tau average is equal to 3 by 2. And for circular section, tau maximum by tau average is equal to 4 by 3, and tau maximum divided by tau NA is equal to 1, and tau NA divided by tau average is equal to 4 by 3. And for triangular section, the tau max divided by tau average is equal to 3 by 2, and tau maximum divided by tau NA is equal to 9 by 8, and for tau NA divided by tau average is equal to 4 by 3. And for a diamond cross section, tau maximum divided by tau average is equal to 9 by 8, and tau maximum divided by tau NA is equal to 9 by 8, and for tau NA divided by tau average is equal to 1. And now we are going to see about the bending or flexural equation. As the assumption we have already seen, the bending equation is m divided by I is equal to sigma by y is equal to E by R. The bending stress sigma is equal to my divided by I, and for the radius of curvature R is equal to EI by m, and for curvature of section is equal to m by EI, and flexural stiffness EI divided by L, and section modulus I divided by y, and flexural rigidity is equal to EA. And now we are going to see about the torsional equation, which is T divided by J is equal to tau max divided by R is equal to G theta divided by L, and torsional rigidity is equal to GJ, and torsional stiffness is equal to GJ by L, and torsional flexibility is equal to theta by T, and polar torsional section modulus is equal to ZP is equal to J by R, and strength of solid shaft tau max is equal to TR divided by R, TR into R divided by J is equal to 16 TR divided by pi d cube, and power transmitted by a shaft P is equal to T omega is equal to 2 pi nt divided by 60, and strength of hollow shaft TH is equal to pi divided by 16 tau h with the whole bracket of d power 4 minus capital D power 4 minus small d power 4 by capital D. When a shaft is subject to torsion and bending, the following formulas we have to remember as: bending stress sigma b is equal to 32 m divided by pi d cube, and maximum shear stress tau max is equal to 16 t divided by pi d cube, and maximum bending stress tau max divided by tau sigma max divided by tau max is equal to 2 m divided by t, and maximum principal stress sigma max is equal to 16 by pi d cube with the whole bracket of m plus root of m square plus t square, and the bracket closed. The minimum principal stress sigma minimum is equal to 16 pi d cube with the whole bracket of m plus root of m square plus t square, and the maximum shear stress tau max is equal to 16 divided by pi d cube with the whole bracket of it's a whole square root of m square plus t square. Equivalent bending moment me is equal to 1 by 2 m plus root of m square plus t square. Equivalent twisting moment T E is equal to whole root of m square plus t square. And the strain energy for various shaft: for a solid shaft, US is equal to 1 by 2 t by t into theta is equal to 1 by 2 t square L divided by GJ. This also is equal to sigma tau square divided by 4G into volume of shaft. Hollow shaft UH is equal to 1 by 4 into tau square divided by G, do square plus di square divided by do square into volume of shaft. Shear stress is equal to U is equal to tau square divided by 2G into volume, and the ratio of strain energy for UH divided by US is equal to do square plus di square divided by do square, and ratio of torque for TH divided by TS is equal to do power 4 minus di power 4 do power 4. The maximum shear force bending moments on slope and deflection, which are formulated as a simply supported beam with point load at center is plus or minus W by 2. It's plus W L by 4. It's W L square, and the slope was W L square divided by 16 by EA, and the deflection was W L power cube by 48 EA. The simply supported with the UDL, the maximum shear force was plus or minus W L by 2, and the maximum bending moment was W L square divided by 8, and the slope was W L power 3 divided by 24 EA, and the deflection was 5 W L power 4 divided by 384 EA. And the cantilever beam with point load at its end, the maximum shear force was minus W, and the maximum bending moment is minus WL, and the slope is WL square divided by 2 EA, and the deflection is WL power cube divided by 3 EA. And the cantilever beam with UDL, maximum shear force is minus WL, and the maximum bending moment is minus WL square divided by 2, and the slope is formulated as WL cube divided by 6 EA, and the deflection is formulated as WL power 4 divided by 8 EA. And the gradually varying load 0 at free end and maximum at fixed end the maximum shear force is minus WL by 2, and the maximum bending moment is minus WL square divided by 6, and the slope is WL power cube divided by 24 EI, and deflection WL power 4 divided by 30 EI. And for cantilever beam with the moment at its free end, the maximum shear force at 0, the maximum bending moment is M, the slope as formulated as ML divided by EI, and the deflection is formulated as ML square divided by 2EI. And now we are going to see about the different formulas used for column. Sigma max is equal to P by A, the whole bracket of 1 plus 6E divided by B, and sigma minimum is equal to P by A, the whole bracket of 1 minus 6E divided by B, and the slenderness ratio lambda is equal to 1 LE by K minimum, and the K minimum is equal to root of I minimum divided by A. And for maximum limit of eccentricity in a solid rectangular section, the shape of core is rhombus, and for a square cross section the shape of core is square, and for a solid circular section the shape of core is equal to circular, and for a hollow rectangular section the shape of core is rhombus, and for a hollow circular section the shape of core is circle. If the slenderness ratio is less than 32, the type of column is sharp column and falls in crushing. If the slenderness ratio is between 32 to 120, it's called intermediate column, and fails in combined crushing and buckling. If the slenderness ratio is greater than 120, it is classified as long column and it fails in buckling. As per Euler's formula, the buckling load or crippling load is equal to pi square EA minimum divided by L square, which is also known as pi square EA divided by lambda square. For Rankine formula, 1 by PR is equal to 1 by PC plus 1 by PE. The crushing load is PC is equal to sigma C into A, and for PR is equal to sigma C A divided by 1 plus alpha L square L by K whole square. The Rankine constant is sigma C divided by pi square E.